Hi, everybody. Welcome. It's Tuesday. Ignore the whiteboard. I'm recording this on Monday. So today you're going to go to modules. If you are virtual, you're going to complete today's assignment in Kami. If you are choosing to complete the assignment in your science workbook, you're going to need to take a picture of your completed workbook pages and submit those to me in the inbox. Make sure that the pictures are clear enough so that I can read your writing, so that I can give you credit. I can't grade what I can't read. Or you can turn in that assignment through the office. You can just tear the pages out and turn it in that way. It's fine. So you'll scroll down to Tuesday. Today we're completing activity 3-2, more objects that begin moving. And this assignment starts on page 32 and ends on page 35. This is going to be part A, part B. So we're going to do half of it today in class, and then we'll do the other half tomorrow. This lesson video is for the full activity. So you're going to open your science workbook to page 32. Based off of what we learned yesterday, we determined that objects do not begin moving until a force is applied to them. So your marble, your tennis ball is going to stay at rest. It's not going to go into motion, and it will stay there forever until something applies a force to it. So it's forces that cause motion. And then so today we're going to consider other objects that begin moving and to verify whether this statement is true or not, if it's true in all circumstances or if it's only true for some circumstances. If you have a tennis ball or a basketball or a soccer ball at home, then you can do this activity at home. If not, then you can continue watching the video, and I'm going to show you someone else interacting with those objects. If you're choosing to do this on your own, then you can just fast forward to that next part of the video where we go to part B. While you're doing part A, I want you to make observations. What's happening? Why is this happening? How much force am I applying? What distance is the ball traveling? How is the ball moving? How is the force applied? What applied that force? So just make observations based off of what you see within the experiment. So the first time, so you're going to have a ball. And you need a partner. So you need a sibling or an adult that's at home to do this. So you're going to sit kind of like you're just rolling a ball between each of you. You can sit on the ground. You can sit at a table. But you're going to push the ball and you're going to move it away from you and towards your partner and make observations on how that ball moves. Apply more force, apply less force. What happens to the speed of the ball and the distance that it rolls when you apply more or less force to it? What happens when the ball moves away from your partner and towards you? So they're going to push the ball back. Same thing. If you apply more or less force, or what are you applying that force with? And then can you and your partner apply a force to the ball so that the ball does not move? Both of you are applying a force, but you don't want the ball to move. How could you do that? Okay, so we're going to watch a video of two partners interacting with their object and doing these things. Where am I going? So make observations on the ball. The ball is currently at rest, and it will stay at rest. So we have two people applying a force. Does the ball roll? Why doesn't the ball roll? What kind of force do you think each person is applying? What direction is that force going in? What are the components of this system? The ball is able to move towards one of the people. So what does that mean for the person that's pushing the ball? What are they doing? To get the ball to move to the left, the person on the right has to do what? Same thing. The person on the right has to do this to get the ball to move left. Okay, so let's look back at our notebook. You're going to complete the interactions table and then construct a model that represents all of the components within this system. Okay, so the first thing we need to do is create our table. We know that the objects in our table, or the components of this, is a ball, There are two different people, so I'm going to say hand 1 and hand 2. There's a table, and this system is interacting on Earth. So these are my components. I need to make sure that I list them in the same order. So we have ball, hand 1, hand 2, table, and Earth. Okay. If our objects come in contact with each other, or if they are applying some type of force, either a contact force or a force at a distance, we're going to use a plus sign. If they are not in contact, they are not applying any kind of force to each other, we use a minus sign. And the ball can't interact with itself, so we put a slash. The hand can't interact with itself. Here's my chart. Let's start with that. So does the ball interact with hand 1? Yes. Hand 2, yes. The table, yes. Earth, yes. Earth is pulling down on the ball from gravity. Now, the ball is also pulling back up on Earth, but because Earth is the larger object, it has more mass, it has more gravity, it has a stronger force, it wins in this tug of war. Hand one and the ball. Hand one and hand two, are they physically in contact with each other? Are they applying some type of force at the distance? The answer is no. The hand and the table also do not come in contact. The hand and Earth do. Hand two and the ball does not interact with hand one, does not interact with the table. It does interact with Earth. The table and the ball, yes. The table and the hand, no. The table and the Earth, yes. And then Earth pulls on all of these objects because of gravity. Or the gravitation, or Earth's gravity pulls on all of these objects. So that's our chart. We're also going to use this chart to create our model. And then anywhere there's a plus sign, that is a force arrow. Okay, so this is our free body diagram. We're going to build it from the bottom up. So at the bottom, we have Earth. Sitting on top of Earth is the table. Sitting on top of the table is the ball. And on either side of the ball, in contact with the ball, is hand one and hand two. So everywhere there's a plus sign here, I'm going to have a force arrow here. Remember, my force arrows are solid if they are in contact with each other, and they're dashes if they are forces that are working at a distance. So the hand and the ball are in contact, the ball and the hand are in contact for both hand one and hand two. The table and the ball are interacting with each other. The table and the Earth are interacting with each other. The Earth is also pulling on the hand, and the hand's pulling on Earth. The Earth is pulling on the ball, and the ball's pulling back on Earth. Same thing for hand one. And notice that our table and hands are not in contact. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 arrows. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 force arrows. Now, this is an even number because forces come in pairs. In opposite directions. Forces come in pairs in opposite directions. All right, so let's take a look at our questions. These questions start on page 33. What are the 4 forces that act on the ball when it lies on the table and is pushed by you and your partner? There are 4 forces. So I've got 4 pairs of arrows. 1, 2, 3, 4. Those are the forces interacting with the ball. So hand 1 and 2. The table and Earth. The table, Earth, and the hands apply a force to the ball. Which forces do you think influence the ball's horizontal motion? That's moving from left to right, like you're on a horizon. Okay, so what is causing the ball to move left to right? And that's the hands. The hands push the ball horizontally. Why do the others not affect the horizontal motion? The earth is pulling down, and the table pushes up. That's vertical motion. What happens if the force applied to the ball by your hand is greater than the force applied to the ball by your partner's hand? We have to explain. So one force is greater than the other. It's just like the tug of war between Earth's gravity and the tennis ball's gravitational pull on the Earth. It's this tug of war that happens. Okay? The larger force is going to win. So, because I apply a greater force than my partner, the ball will move what direction? Away from me. Because it was a push force. You're pushing the ball, so it's going to move away from you. So if we think of it like this, so I'm pushing on the ball is pushing back, but my partner is doing this. It's a smaller force. This is a small force. This is a large force. It's going to move in the opposite direction. So if I'm pushing, it's going to move in that direction. It's going to be pushed away. This is motion. Suppose the ball was pushed with both hands, but hand 1 pushed harder than hand 2. The ball responds a certain manner. Can you get the ball to respond in the same manner while pushing it with only one hand? If yes, which hand should you push the ball, and how hard should you push it? How hard should your partner push it? Let's try this again. How hard should your partner push? So only my partner should push the ball. But not as hard as before. Okay, so let's say that we've got, let's say 30 newtons of force here, and am I pushing that way? Whoops. And we have 15 newtons of force here. The ball is going to move in this direction with 15 newtons of force. Okay? If I still want to get the ball to move in this direction with 15 newtons of force, I can apply 15 newtons of force here, and my partner doesn't push on it at all, doesn't apply any force. And the ball is still going to go in that direction. I just have to apply less force on both sides. how hard must each of you push to keep the ball motionless? Okay, so if one person is pushing harder than the other, we get motion. Both people need to push on the ball at this with the same force. So both people push on the ball with the same force. Okay, so here's my ball. Okay, let's say that this person is pushing with 15 newtons of force, and this person is pushing with 15 newtons of force. If I'm pushing you, you pushing me, or pushing at the same with the same amount of force, then there is no motion. Regardless if that number is 15 or 30 on both sides. It's balanced. As long as it stays balanced, we're good. Okay. Then at the end of the video, we saw that they were holding the ball above Earth and then they dropped it. So we're going to draw a free body diagram of a ball that is held in your hand before it's dropped. Okay. So we know that the Earth is down here. Okay. Here's the ball. My hand is going to hold the ball up. Earth is trying to pull the ball down. This is what's happening before it's dropped. If there's no motion here, then my hand and Earth, the forces are balanced. There's no motion. Until I let my hand go and the ball is pulled to Earth. Okay, let's look at our making sense questions. When do two forces that are applied to an object counteract each other? They cancel out. When do they cancel out? Forces counteract each other when they are applied to the same object in opposite directions. Okay, so if I have an object like a ball, and I have a hand pushing in this direction, and I have a hand pushing in this direction, this hand is pushing at 30 newtons, but this hand is pushing at 15 newtons. I'm going to subtract the force. So 30 minus 15 is 15. The larger force wins, and this ball is going to move 15 newtons in that direction. If I have a ball and the hand is applying a force on this side and the hand is applying a force on that side, let's say that this is 15 newtons and this is 15 newtons. We have opposite arrows, so these forces are working against each other. So 15 minus 15 is 0. If I have 0 newtons of force, then there is no motion, and my forces are balanced. two forces that are applied to an object reinforce each other? When forces are applied to the same object in the same direction. So if I have a ball and I have one person hand that's pushing on the ball in that direction, and I have another person pushing on the same ball. So if I push with 15 newtons of force and they push with 15 newtons of force, then our forces are going to work together. They're going to reinforce each other. And my ball is going to move in this direction at 30 newtons. 15 plus 15 is 30. When do two forces that are applied to an object cancel each other? Forces cancel each other when they are equally strong applied to the same object and in opposite directions. So if I have a ball and I have 15 newtons here and I have 15 newtons there, they're going to cancel each other out. We have 0 newtons. They are balanced with no motion. And then question 4. An object applies force to several other things around it. Do you think that these forces influence the object's motion? Object applies force to several other things around it. Do these forces influence the object's motion? So an object's motion is is influenced only by the forces that are applied to it, not by the forces it applies to others. Okay, so if I push a ball at 15 newtons, and that's going to cause my ball to go into motion at 15 newtons. because I'm influencing its motion. I'm that outside force. Tomorrow we're going to do an extension activity with a heavy duty shopping bag and look at the forces that are interacting with something as simple as a grocery bag. Okay. I'll see you tomorrow.